So we left off last time having introduced the notion of logging as a mechanism for recovering from crashes of the database. And we talked about our goals for recovery, that if the power should go out or the machine should crash for some reason, we wanted to be able to redo the effects of all the transactions that had reported commit and then abort everything else. Anything that reported abort or anything that never reported anything at all should be aborted. And we said that the trickiest part of dealing with recovery was when we take an aggressive view of how we want to handle the buffer manager. Because after all, the buffer manager is the place where things that were on disk got pulled into memory and started getting manipulated, but haven't yet been committed back down to the disk where they're safe, right? And so the deal is there's kind of two ways to think about this. First of all, when a transaction commits, there's the question of, do we force the transaction to push all its pages out of the buffer pool to disk before it commits? All right, before it reports commit. If we do that, we call that a force policy. Make sure that every update is on the database disk before commit. All right? So that provides durability without any redo logging because, of course, by the time you tell the user commit, all their stuff is safe in the database. Okay, but this can obviously cause poor performance because every transaction at the time of commit has to run around writing their random disk pages to random locations on the disk. All right, so the force policy we would like to actually make not a force policy if possible for performance reasons. The other piece of the puzzle has to do with undo, which is the no steal policy. So if you want to make life easy for undo, you can say that once you dirty a page in the buffer pool, it's not allowed to be written to the disk until commit time. If you say that, we call that a no-steal policy. I, as the buffer manager, am not able to steal away a buffer frame from you, the transaction, until you, the transaction, commit. Okay? So we don't allow buffer pool frames with uncommitted updates to overwrite committed data on the database disk. This is nice because if you crash, there's no dirty data on the database disk, right? Which means there's no undo required when you recover. So that would be nice, but that can also cause poor performance because you have to keep around these dirty pages in the buffer pool until commit time, and that might be a very long time from now. And in the interim, you're filling the buffer pool up, right? And there may be pressure from other transactions to want pages in the buffer pool. Moreover, from a performance perspective, you want the buffer manager to be able to figure out what it wants to write to the disk when. Right? For highest performance, we should have that buffer manager being very aggressive about putting things on disk when it's convenient. So in practice, we're going to need to, pick a pretty aggressive space here and then somehow make it work. So what we really want is steal and no force. Okay? It's going to be the most complicated scheme because we're going to need to deal with both redos and undos when we recover. All right? But it's going to give us the highest performance in the steady case where things are not failing. Right? I am slightly puzzled by this underline here. I think it's a typo. It's a PowerPoint effect. But no force is what that first underline should say. No force. All right? So we're not going to make people or transactions force their buffer pool pages to the disk before they commit. So they'll be able to commit to the user. The user will think that everything's good. Database will crash. When the database comes back up, it has to observe that durability contract. It has to redo the effects of the transaction. So what if the system crashes before, before the time that a modified page of a committed transaction makes it to the database disk? Somewhere, somehow, we have to record the information that would have been written so that we can redo it. Right? It's not in the database. We're going to have to write it down somewhere. And where we're going to write it down is in a log. And we're going to write down as little as possible in a convenient place, which isn't too expensive to access, for our redo information. So we'll have some redo information in a log that's cheaper to write to than the actual database page. Okay? And we'll make sure that all our redo information is written into that log before we commit. But we won't make sure it's in the database before we commit. So it's sort of you're writing somewhere else instead of writing to the database. And then the steal policy complicates enforcing atomicity because if a transaction that had performed updates aborts, its changes may actually be in the database. That's what steal means, is that we took buffer pool pages, wrote them back down to the database. They had uncommitted data on them. In that case, we have to undo that action. And the way we undo it is we make sure that we remember the old value of that page before this dirty write went to it somewhere in a log. Okay, so this log is going to hold redo information for dealing with no force. And it's going to hold undo information for dealing with steal. And by correctly capturing these redos and undos, we'll be able to recover and then guarantee durability and atomicity. Ooh, I have a battery issue. Interesting. Does anybody have a recent Mac power plug? Thank you. Don't forget to get it back at the end of class. Awesome. Thanks very much. Super. Okay, so this is the design space. All right, if you look at force versus no force, steel versus no steel, the fastest place to be is in the upper right. We're steel, no force. That's what we want to do. And if you think about the logging and recovery implications, the lower left was the easy thing, force and no steal. If you force things before transaction, then you have no redo. If you don't ever steal things, you have no undo. Right? And you can see how they changed, based on the choices you make. And so you should understand this relationship between redo and force, undo, and steal. You should understand how those fit together. We're picking the upper right, which is the most aggressive, where we have to do undo and redo information, because we're stealing pages and not forcing them at commit time. So the basic idea is, where are we going to write this stuff down? We're going to write it in something called a log. We're not going to write things into the database, but we are going to write things into a log. So we're going to record the redo and undo information for every update that we would make to the database into a log. And the log is going to be on its own disk, particularly back when we're using magnetic devices, if you have very large systems, or if you're living in a magnetic device universe, if you're cheap or you're living in the past. The nice thing about having it on its own device is that you have its own disk arm. And so updates to the database are not jostling the log device disk arm. The log device mostly is just appending to the end of the log. Okay? So it's cheap to write because it's mostly sequential I/O. All right, so the logs are going to be on a separate disk. And then we're going to write as little as possible to this log. So we're not actually going to form a proper database page the way we would in the database. We're going to write just a diff of some kind, either a literal bit diff or maybe some sort of semantic diff. We're going to write the minimum amount of information we can to this log to enable us to undo or redo, depending on what kind of log record it is. And this is going to allow us to get multiple updates, which might have been multiple IOs to the database, are going to all be accumulated and written in a single IO to the log, because these updates are going to be little, and we'll be able to coalesce them together, even though they relate to different places in the database. Okay, what is the log? Well, it's going to be a list, in essence. It's an ordered data structure of redo and undo actions. All right, and the simplest way to think about the log records, there's going to be some extras, but the basic log record has the following information. It has a transaction ID. Which transaction generated this log record? It has a page ID. What physical database page is this log record referring to? Is it offset on that page? Where from the beginning of the page is the change? The length of the change. So how many, what's the extent of bytes that got changed? And then the old and new data for that change. So that's just a diff, right? The offset length, old data, new data, page ID. All that stuff is a physical diff of a database page. Now there's other ways to do logging, but this is the simplest way to think about it, is physical logging of just byte differences, and a simple thing to get your head around. So we'll just assume this is the kind of logging we'll do. And because we write both the old data and the new data, you can use it for redo or for undo. Okay? There's going to be additional control info in the log, which we'll see in a minute. But this is the basic idea. Any questions so far? We haven't said much yet, but any questions on the format of the log? Yeah?
Is there a reason you couldn't put the actions that we didn't have to do that on the same stage?
Yes. So there's various tricks you can do that would perhaps save space. I'll give you an example. Suppose you're doing an insertion into a table, and along the way you also update a B-tree page. In principle, you don't really need to remember you updated the B-tree page. You could just remember you inserted this tuple. The B-tree page update, you'd figure out you needed to do when you played redo, right? So you don't need a physical diff of the B-tree. You just need this semantic diff. I inserted this tuple. So that would be called logical logging. So you're not logging the actual bytes that changed in the database. You're logging the action you took to the database. And there are various tricks like that you can play, but we won't do that here because there's enough complexity in the way I'm going to describe Aries, which is this logging protocol, that we'll just stick with physical diffs. Right? And there are various subtleties with logical diffs, undo versus redo and stuff, so I don't want to get too complicated with that yet. Good question, though. Very natural question. Healthy.
So if two structures change, does that mean the whole the B tree and the things that you don't have
Yeah, so for now, well, no, because there are different pages in the database. You have 2 separate log records, one for each diff, right? Is that a question? Just a scratch. Okay. Any other questions? These are good questions. Clarifying questions. All right, the key idea is on the next slide. So the key idea is what's called write-ahead logging. Okay? Write-ahead logging has 2 rules. You have to have both of them to do it right. The first is you must force to the log device the log record for an update before the corresponding data page gets to the disk. Or to say that the other way around, you're not allowed to write something to the database unless its log record has already been written. So you log first, which is to say you physically make sure it's in the log device, and then you can force to the database disk. Good? That's why it's called write-ahead logging. And the second one is that before you report commit on a transaction, you must force all log records for that transaction. You're not allowed to send a commit to the user level until you're sure that all of their log records are on the log disk. The first of these guarantees atomicity. It guarantees that you can undo something in the database because you know it's in the log before it hits the database. Dirty data in the database has corresponding undo information in the log. Right? The undos hit the database. Sorry, the undos hit the log before the data hits the database. The second of these guarantees durability. The redo information hits the log before you tell the user about commit. Got it? So that's the write-ahead logging protocol. And with the write-ahead logging protocol properly implemented, we can have steal no force buffer management and feel good about our transactions. Now there's a bunch of subtleties which we're going to go through. And so the exact details of logging and recovery, we'll look at the Aries algorithms, which were pioneered at IBM in the 80s and have been used in some form in most transactional databases up till recently. So we'll go through those. But this is the basic idea. Any questions about this? Super important that you understand this interplay between the buffer manager stealing pages and then the first part of the write-ahead logging protocol, right? You stole a page. Before you write that page to the disk, you have to write the log record that would allow you to undo it. And then the force policy, because we're doing no force, we do have to force the log before we commit, but we don't have to force the database pages. And that will, by forcing the log, we can redo the updates of that transaction upon recovery. Right? So all those things go together. All right. Now we're going to dive into the details, and they are detailed, because to get this right has proved very, very tricky over time. And what we're going to do in this class is we're going to walk a very narrow path down a correct protocol that works, okay? And it's going to make sense. As we walk down that very narrow path, you're going to ask the question in your mind, I bet, what if we did it this way? And what I'm going to warn you is that there's all sorts of ways to fall in the pit on either side of this path. There may be another path, all right? You may be able to invent a new protocol, but be warned, it's very complex. And so as a matter of education, it's very useful to just learn one protocol that works, which is Aries. And then I invite you to invent your own protocol that maybe you think will save IOs during logging or during recovery, and perhaps you'll invent a better one. But very often when people try to tweak this protocol, it breaks in some funny corner case. So I'm going to teach you just the protocol. If you take the graduate course in databases, we'll get you to read the Aries paper, which is about 75 pages long. And every time they introduce an idea, they say, now suppose you did it this other way. Here's all sorts of bad things that could happen to you. But it makes it very hard to read that paper and understand actually how to get it right. So we're just going to talk about how to get it right. But if you ask too many questions, you're in for a 75-page research paper. Okay, I'm just warning. All right, so I won't entertain a lot of those questions today, unfortunately, because the design space is too big and too fraught with peril. All right, so we're going to take one path through this that works, and then if you want to come to office hours and chat about ideas, I'd love that. But today we'll just do Aries straight up. All right. So here's kind of a big picture of write-ahead logging and the way the log works. There's 3 places that data can live, so to speak. It can live in the log, it can live in the database, or it can live in the buffer pool in RAM. Okay? 3 different devices, in fact, physically. All right. And in each of these places, we're going to have to link the information together. What's in the log, what's in the database, what's in RAM, and how do they connect to each other? And the identifiers that we'll use to connect these are called log sequence numbers. All right, and they are the IDs of log records. So every log record is going to have a unique log sequence number, or LSN, and we'll just assign them in increasing order as we write things to the log. All right, so it's just the page number in the log sort of from start to finish, but it's not necessarily a physical page number. It's just a number, increasing every time you add a log record, log sequence number. In the database, each data page, each page of your database, the real database, is going to have a page LSN written on it. What is the page LSN? It's an LSN of the most recent log record that updated this page. So it's a pointer to the log. Every database page has a pointer to the log record that most recently modified it. It's the page LSN. Make sense? Okay. So there's a picture of the page down at the bottom with the page LSN pointing to the log, which is going from top to bottom in log sequence number order. The system in memory is going to keep track of the flushed LSN, which is the maximum LSN that so far has been flushed to the log device. So if you think of the log as a sequence of pages going from top to bottom here, the blue pages are the ones that have already been forced to disk. The flushed LSN points to that last one that's been flushed. And then there's this thing still in memory, log records that have yet to be flushed to the log, which we'll call the tail of the log. All right? And that hasn't been written to the log yet. It's waiting for a good time to do some I/O to the log. Right? And at any given time, there's some log tail in RAM. And another way to talk about the write-ahead logging protocol is in terms of these variables. You can say before page I is written to the database, the log must satisfy the property that the page LSN of I is less than or equal to the flushed LSN. That is to say, the log record for this page is not in the tail. It's above the flushed LSN. Make sense? You can't write this page to disk unless its page LSN is in the part of the log that's been flushed. That's just write-ahead logging. All right, it's the first part of write-ahead logging. I can. Let's do it pictorially. Here's a picture of a database page in the buffer pool. It's got a page LSN that points to the log. Suppose that page LSN points to the log tail, to the black part. All right? If it pointed to a log record in the log tail, that would mean that this is in the memory, and so is its log record, its most recent update. So it's a dirty page with no log yet. So for write-ahead logging to happen, we have to flush that log record before we flush this page. And we'll know we flushed that log record before this page when the flushed LSN is bigger than the page LSN of this page. Because that means that the line between blue and black is now below the page LSN, as it is in this picture. Right? We just want to make sure that when we write this thing out of the buffer pool onto disk, the page LSN there points into a blue part of this log record, into the flushed part. Make sense? Blue part of this log. So just to make clear again, the picture is showing the log in log sequence number from top to bottom, where top is low values of log records, bottom is more recent high values of log records. By the way, the log has to be flushed in order. You can't skip log records when you flush. You have to flush the log in sequential order, top to bottom. Yeah?
Does flush mean to write to disk?
Flush means write to disk. Yes. Thank you. Other questions? Remember the write-ahead logging. All that we're saying is that pages have to be written after their log records. The log is being written in sequential order. So page LSN has to be less than or equal to the largest LSN that's been flushed to disk, which is the flushed LSN. Good? Okay. So what's in a log record, really? I kind of gave you a gloss, but let's spend a little more time. There's a couple of LSNs in the log that we didn't look at. So there's the actual sequence number of the log record, the LSN. There's also the prev LSN, which is a back pointer. It's a previous LSN. And it's the previous LSN for this transaction. So each transaction's log records are in a linked list from most recent to beginning, backwards linked list of log records. That's what the prev LSN says. Is what's the previous LSN of the transaction that generated this log record? Okay? So that's prev LSN. The transaction ID, XID, is this transaction's ID. Logs actually will come in one of a few types. The ones we've been looking at so far are update log records, which are the standard log records. But there'll be some extra log records we'll look at in a minute. And then if it's an update log record, we have the diff, page ID, length, offset, before image, after image. But other kinds of log records we might have is commit, which is just a log record that says this transaction commits. Abort. Okay. We're going to have a special kind of log record called checkpoint, which we'll talk about in a bit for log maintenance. And then we'll have these funky things called compensation log records, which we'll see in a minute as well, to help us with undo. And then, in addition to commit and abort, we'll also have end. If you think about it, you would expect that aborting is not the end of the story, because after you write an abort log record, you have to undo stuff from the aborted transaction. When you're done undoing stuff, you can write an end log record. So there's also going to be end log records. All right, so just be aware of the different types. We'll now go through how they get used. All right? There's a little bit more state you have to keep track of. There's going to be 2 tables in memory. And the fact that they're in memory should make you comfortable with the idea that they're transient data. We could reconstruct these from the database and the log when we recover. So these aren't critical information. They're just like information we're going to need to do our processing. Okay? But they're recoverable information. So in memory, we're going to keep the transaction table, which has 1 entry per currently active transaction. All right? And that entry will be removed when the transaction commits or aborts. It contains for each transaction the transaction ID. Okay? The status of that transaction. Is it running? Is it committing? Is it aborting? What status is it in? And the last LSN, which is the sort of end of that linked list of log records for this transaction. What's the last LSN written for this transaction to the log? This is not the last transaction, the last LSN flushed to disk. It's the last LSN generated for this transaction. It's probably still in memory. All right? It might have been flushed, but it could well be in memory still. So the last LSN is how you find the most recent thing that the transaction did in the log. All right? So that's the transaction table. What transaction is it? What's its status? And how do I get access to its chain of log records in reverse order? In addition, we'll also have information about what's going on in the buffer pool. That's called the dirty page table. It's going to have 1 entry for every page in the buffer pool that's currently dirty, meaning it's in a different state than it was when we read it from the disk. Dirty here doesn't necessarily mean transactionally dirty. It means it's different in memory than it is on disk. That's what dirty means. It's been changed, and that change has yet to be reflected in the database. Okay? So 1 entry per dirty page table, per dirty page currently in the buffer pool. And there's an LSN here as well. All right, be careful with this one. This is the trickiest one. It's called the rec LSN. The LSN of the log record which first caused the page to be dirty. So think about it. Something gets read off the disk into the buffer pool. It's hanging out. It's all good. Somebody wants to write to this page, and they modify it in the buffer pool. That generates a rec LSN for this page. Okay, so now it's dirty. Someone else wants to make a change to this page while it's in the buffer pool. We do not update the rec LSN. All right, what the rec LSN is, it's the first point in time since this was read that it got modified, where time is defined by the log. All right, so it's the point where it started changing from what was in the database. And it doesn't change as you continue to update it in memory. If you push it back down to disk, it gets stolen. It's gone. Then when you read it back in, it's not dirty now. It's clean in the sense that it's the same as the disk version. And then somebody comes along and modifies it, and it gets a new rec LSN in this table. All right. The rec LSN is the first log record that caused this page to be dirty, which means different than what it is on disk. So this slide is everything you need to know. This is all the state of this recovery protocol. You got your log records, which have LSNs and prev-LSNs to backwards chain them for a given transaction, and the type of the log record, and then for updates, the diff. In the database, you have your data, but remember that every page has a page LSN, which points to the last update in the log to this page. There's a thing called the master record, which we'll see in a minute, okay, on the database too. And then in memory, we have some stuff, all of which is recoverable if the system crashes, okay, in some sense recoverable. But in memory, we'll use it. We've got the transaction table, remember, which has the last LSN for this transaction and the status of the transaction. We have the dirty page table, which for each page has the rec LSN, the first log record that modified it. We have the flushed LSN that tells us what's been flushed to disk in the log, how far down in the log have we gotten as we flush it sequentially. And then in memory, we also have, of course, the buffer pool and the log tail, right? Right, and they're not safe yet. They're floating around in memory. That's everything. That's all our state. What we're ready to do now, having introduced all this state, is go through a steady state, happy, no crashes, no aborts, regular transaction, and see how it manipulates this state. Okay, so let's do that. Normal transaction execution is a series of reads and writes followed by a commit request or an abort request from the user. This is normal, no problems happen transaction. Please assume throughout all this conversation that individual page writes are atomic to the disk, because otherwise you'll make yourself crazy. Okay, that was handled by a lower level of the system, making sure you don't get a page that's half written and half not written. All right, page writes are atomic. You can really, if you go too far down, you're like, wait a second, is a 1 or a 0 on the chip really a 1 or a 0? Because there's like some circuit voltage that kind of goes up smoothly, really, right? And you can drive yourself insane trying to think about all of that from the wires up, right? So we're going to assume disk write is atomic. I promise you there's ways to make that true most of the time to the point where you should ignore it. Disk write is atomic. Strict two-phase locking is in place. All right, you get to rethink all this if you want to do multi-version concurrency control, all right? Which is you want to do anyway, because if you have multiple versions, after all, you might not be updating things in place, and you wouldn't do logging, you'd do something else. All right, but we're going to do strict two-phase locking, which is what most people do. And the most aggressive steal no-force buffer management with write-ahead logging the way we've described. How does the write-ahead logging work? Let's go. At some point, you're following write-ahead logging. So before pages get forced out of the buffer pool, put on disk, you know that you've written the log records for those pages, right? That's write-ahead logging. So before the buffer pool replaces a page and forces updates to the disk, it makes sure the logs have been flushed to the log device. In sequential order. You can never flush a log record until all the ones prior to it have been flushed. Okay. So at this point, it's time to commit. The user says, I want to commit the transaction. And this is where life gets kind of interesting. So what happens is that generates a commit record in the log for that transaction. So transaction ID for this transaction, type of the log record is commit. Prev LSN points to the last LSN for this log record. That's just in memory so far. So far that commit hasn't hit the log device, and so it's not really a commit. You can't return to the user yet, because it's not on the log. So you generate this commit log record. Now, at some point, and this may happen later, at some point, all of the log records up to and including this transaction's commit record get flushed to disk. And maybe that happens because there's a log writing process that woke up and said, I'm going to write the log tail to the disk now. Okay, it doesn't necessarily happen right away. But at some point, log records up to and including this transaction's commit record are flushed, guaranteeing that the flushed LSN, which is the LSN of the largest thing that's been flushed to the device, is greater than or equal to the last LSN of this transaction, because the last LSN of this transaction is the commit record, right? That's the last log record we generated for this transaction, and we just said that its commit record is on disk. Okay, at this point, write-ahead logging has been observed. Log flushes are sequential writes to disk, so that happens in batches for efficiency. We get many log records pushed into a single I/O to that log device. That's all good. At this point, the user's request to commit the transaction returns to them and says, your transaction is committed. Only after the log records have all been written to the disk do we return to that user call to request commit transaction. And you can try this, in Postgres. You can say, begin transaction, run query, update this, update that, commit transaction. When it returns to you and you get the cursor back, you know all this happened. Okay, but it won't return to you until all this happens. At that point, we also generate an end record, and we put it on the log, but that's just in memory. We're safe once we get that commit record to disk. We're also, for bookkeeping reasons, going to want end log records for every transaction. And you'll see why in a minute. Okay? So we'll generate an end log record. So that's regular transaction commit. Any questions? You can see very clearly that we're guaranteeing the second property of write-ahead logging, that we don't return from commit until we write the log records to the disk. Okay. Now let's look at abort. This gets more interesting. This is user-initiated abort. So there's not like the system crashed. There's nothing going on except for this transaction. So let's focus just on this transaction and how we deal with it. All right. What do we want to do? Well, this transaction might have dirtied the database. It might have had some of its updates get flushed to the database device, and we need to undo them. We need to undo the actions of this transaction. So we want to play back the log essentially in reverse order, undoing our updates. Okay, and here's how it's going to work. In the transaction table in memory, we know the last LSN of this transaction because we were keeping track of it. That's the last thing this transaction did. We go get it from the log, which may be on disk or may be in memory. Okay, but we go get that last LSN. We look at it. We write an additional log record. So as we're reading log records, we're writing new ones to say we're about to abort this transaction. right, that abort record to the end of the log. And then we're going to follow the chain of log records via prevel ascend backwards, updating the database to its previous state, undoing these log record changes. The weird thing is, while we're undoing, we're going to be right ahead logging our undos also. So before we change a page in the database and flush it to disk, we will write a log record saying, we're about to undo an action of this transaction. And those log records we generate for undos are called CLRs, compensation log records. Every time we do an undo, we'll generate a CLR first in the log before we flush the undo. So let's go through this in detail. These CLRs are going to help us make this all work. All right. Now, before we go any further, in order to have undo, we're going to modify the data back to its original state, right? So we better have a lock on the data because we're changing it. We're changing it back, but we're still changing it. And this is not a problem. Why is this not a problem? Two-phase locking. We haven't said anything about commit or abort yet. It's strict two-phase locking, which means we hold all our transactions until the end of this transaction. And so because we haven't responded to abort yet, we have all our locks in strict two-phase locking. So anything we changed, we have a lock on, and we can unchange. No one will notice. That's good. All right. Now, before restoring the old value of a page, we're going to write a CLR at the end of the log. So you're logging while you're undoing. All right? And so it's like we're currently undoing this prevel LSN 123, and we're generating a new CLR, which has the last LSN of this transaction, over at the end of the log. Okay? And the CLR is going to have one extra field that we didn't see in the previous log records, just to make your life more miserable. It's called the undo next LSN. What is the undo next LSN? The undo next LSN is the prevel LSN of the log record we're undoing. It's the thing we have to undo next. So this log record right at the end corresponds to this one we're undoing, and it keeps track of what does this one say should be undone next, which is its prevel LSN. And that's this guy's undo next LSN. Right? 1, 2, 3, 4, 1, 2, 3, 4. Make sense? So the undo next LSN is a copy of the prevel LSN of the log record that this thing is undoing. Okay? The CLR, which after all is an undo record, it's recording an undo, contains only redo information. Because we will possibly crash before we succeed in flushing the database page corresponding to this undo. It could happen that while we're undoing this transaction, we write that CLR and we crash. And when we come back up, we have to know that we were in the middle of undoing this transaction. So what do we do to undo this transaction? We redo the undo that we tried to undo before. Okay? So the CLR wants to put in the original version of this data. And the undo is trying to put back the original version of this data, which came from that log record over there. And so what we're going to write over here is the original version of that data, right? And when we wake up from a crash, we'll redo, put in the original version. Right? So it's redo only information in the CLR. You never undo an undo. Because, of course, you want your undos to succeed. So you redo your undos only. So CLRs are never undone. Undo actually doesn't even have to be idempotent. That is to say that if you apply undo twice, it could do the wrong thing. We're going to make sure we apply our undos exactly once in our protocol. Okay? They might get redone when we're repeating history, but it won't have the effect of doing them twice. It'll have the effect of doing them exactly once. So we'll do this bouncing down our prevel LSN chain, generating new CLRs until we run out of prevel LSNs. We'll get to the first LSN of this transaction, and its prevel LSN will be null. And yay, we've undone all the log records of this transaction. At which point, after the last CLR over here, we can write an end log record. That demarcates in the log the fact that we now have no more undoing to do for this transaction. Got it? So while we're undoing, we're logging what we're about to undo. You always flush that log with write-ahead logging. So you flush the log of CLRs before you can flush any of the database pages that you undid. Right? Write-ahead logging still applies, which means that the log always has a complete record of all the undos that succeeded and possibly some undos that you need to redo. Okay. So far we haven't crashed, but I've given you some concerns about crashing. Yes?
Yeah, so this is very good. When you do an undo, you undo the most recent thing all the way back to the last one, right? In that order.
in reverse order of time, right? And that means that if you update something 4 times, you get it to version 3, version 2, version 1, and by the time you're done, it's an original version. Other questions? Kind of simple. There's a bunch of LSNs being kept track of, but you're really just undoing things in reverse order and writing about it in the undo log with the CLRs. Okay. All right. Before we do crash recovery, which is really what we want to do at some level, right? This whole thing's got to survive crashes, not just simple aborts. But before we do crash recovery, a really important issue is what's called checkpointing. So checkpointing is going to happen all the time, not just for crashes. So here's the thinking behind checkpointing. Conceptually, you have the database and you have a log of all history ever. Right? That's a nice idea, but boy, you don't want to replay the log of all history ever if the database device fails. Right? Or when you're recovering, you don't want to have to recover from the beginning of time generally. So we really don't want to have just the log of the database. We might want to periodically take a checkpoint of the database, like everything in it, and make a copy of it so that we can start recovering from the checkpoint, not from the beginning of time. So that's the idea behind checkpointing. Problem is, of course, you have a database. It's like, 100 terabytes big. Like, you're not going to lock everyone out of it, take a checkpoint copy of it, write it over here on an entire 100 terabyte backup, and then, unlock the database. So you need to find a way to do some sort of fuzzy checkpointing where while you're working, you're squealing out little bits of checkpoint out the side and somehow maintaining something that you can recover from. So Aries has a very clever checkpointing scheme that has the moral equivalence of checkpointing but doesn't actually make a checkpoint copy of the database. So how is this going to work? Well, here's how it's going to go. Periodically, we want to create a checkpoint, but this is all a checkpoint in Aries contains. We're going to write to the log the following. Begin checkpoint. All right, this is the demarcation in the log that this is the log time. This moment in LSN time is the time when we started checkpointing. And then actions might happen, other transactions are going, and then we write one more log record, which is an end checkpoint. What does that end checkpoint contain? It contains the stuff that was in memory. So that's the transaction table and the dirty page table. That's all we're going to checkpoint. Because everything else is on disk. It's either in the database or in the log, right? The only things we should need to checkpoint are the volatile things, the things in RAM. So it's a nice idea, right? It's like, don't checkpoint the whole database. You already have that. Just checkpoint the stuff that's in memory. Cool. But you will notice that we did not lock memory, that we wrote begin checkpoint, and then stuff was changing, and then we were reading these memory data structures, and we wrote end checkpoint. So that's interesting. What we're saying is that the checkpoint we actually write is some smeary version of the main memory data structures between the time of begin checkpoint and the time of end checkpoint. So we have to be a little conservative about it. It can't be older than begin checkpoint. That's good. But it may not be as up-to-date as end checkpoint. So there's a little bit of slop. All right, but the nice thing about that is we don't have to have checkpointing stop other transactions while we're copying these data structures out of memory onto log records. All right, so what do we know? Other transactions continue to run. These tables are accurate only as the time of begin checkpoint. They're actually later than that time. There's no attempt during checkpointing to force the buffer pool to disk because, after all, that information's in the log. Right? Anything about dirty pages in the buffer pool is either in the log or it's going to abort anyway, and it doesn't matter. It's in the log tail. So the effectiveness of the checkpoint is limited by the oldest unwritten change to a dirty page. That is to say, anything that's not in the database and gets written to disk is not somehow in this checkpoint. And that'll be okay because it won't be committed. We're going to store the LSN of the most recent checkpoint for recovery purposes in a safe place. Where's that? We're going to call it the master record. How would we know where it is? Like, we're going to turn the machine on and we'd be like, oh crap, we've crashed, we have to recover. Better start from a checkpoint. Where is that checkpoint? How do I find it? Think of a dumbass scheme to do this. Anybody? Write it somewhere, like where? Maybe the first page of the log device, like page 0. Okay. So there'll be one place that is just the software is going to assume is a constant, which is where the master log record lives. Right? And if you're smart, you replicate it. So it's like at the beginning of the log device, at the end of the log device, or something. Or it's in maybe 2 different devices. Right, but the master log record is just going to be stored somewhere, and all it's going to have is the LSN of that last checkpoint. That's where we're going to start recovery from. We haven't seen how to use the checkpoint yet, but the flavor of it is that we've captured those main memory data structures on disk, and we've time demarcated them as being later than begin checkpoint. We don't know exactly when later, but later than. Okay, we are now ready to do the fun part, which is crash recovery. So this is kind of the big enchilada of Aries, right? Because it's going to do what abort did for transactions that failed, and it's going to redo the transactions that succeeded. And it's going to do all of that in batch because a whole bunch of transactions just failed. The system crashed. And a whole bunch of transactions need to be redone. And we don't want to do this one transaction at a time. We want to do it all the transactions at a time. So it's kind of a batch undo redo protocol for guaranteeing that all the undos happen, all the redos happen, and everything works. So the first thing we're going to do is start from a checkpoint record, which is found from the master record. And really what we want is an end checkpoint record, because that's the thing that has the interesting stuff on it. But we're going to need the begin checkpoint record too. So you can either go from end and roll backwards to find begin, or you can go from begin and roll forwards to find end. It's in the log nearby. Okay. So we get those checkpoint records, and here's the deal. The first thing we do is we read the log from begin checkpoint to the end. That's the analysis phase, A. So if the log records are going down the board in order of log sequence number, the I.O. pattern is you get that last checkpoint, the first phase you do is analysis, and you read from last checkpoint to the time of crash. And in that analysis phase, you figure out the stuff that was in memory at the time of crash. You figure out what was in the dirty page table, what was in the transaction table. You reconstruct it from the log, the database, and the checkpoint record. Okay? Once you've done analysis, you know which transactions committed and which transactions failed. Either they aborted or they weren't committed at the time of crash. Once you know that, you're going to redo all the committed transactions. All right? And then you're going to undo all the uncommitted transactions. Now, what log records do you have to read for these things? For redo, we have to start from, oh boy, everybody wake up. All right, take a stretch. This is the part where we have to start actually like putting it all together and synthesizing. So, take a minute. All right, everybody up. Get up, get up, up. Jumping jacks. 1, 2, 3. Good. Sit down. You're done. Your blood is flowing. All right. Before we do this, in fact, it is now 2:52. We're good. Let's go back here. This is all the state of the database that could exist. Log records, which have LSNs and pre-LSNs, right? Linked list backwards of transactions. The database pages, which have page LSNs that point to the last update. And, okay, be careful. In memory, we have the transaction table. For every transaction, what was the last log record for that transaction? We can recreate that during analysis. We roll forward from the checkpoint. The checkpoint contains a copy of the transaction table in the dirty page table. We're going to roll forward in the log and fill in the last LSN for every transaction as we see it. As we look at those log records, we'll update those last LSNs. So at the end of analysis, we know really the last LSN that got flushed for every transaction. Good? Good? Last thing, the dirty page table. Remember what that is, the rec LSN. That's the oldest update to that page. It's the first update that changed the page in memory that's not in the database. We can also reconstruct that during analysis because the database page is going to have a last LSN on it. And we're going to read the log forward, and we're going to see if we see an update to that page. And the first update we see to that page is the rec LSN. So we know the rec LSNs of the dirty page table. We know the last LSNs. Now, this is the part I wanted you to be awake for. Going back here, crash recovery. What's the oldest thing we need to redo? It's the first and oldest dirtying of a page that never made it to the database, right? The oldest thing that needs to get redone is the oldest thing in memory that never made it down, which is the oldest rec LSN after analysis that we found. So we start redoing from that oldest rec LSN. That's the oldest thing that we could possibly need to redo. And we're going to go through the log and redo everything. This is called repeating history. And one of the beautiful things about Aries is, and this is where we're walking that narrow path, we're going to redo everything. Don't think about, hey man, you don't need to redo that because there's some trick you'll play during undo where you're going to undo it anyway, so don't redo it because you're about to undo it. Don't go there. Really ugly. Just redo everything, okay? And we're going to get to the end of the redo phase, and we're going to have the database essentially in the state it was in at the time of crash. At which point, we already know how to undo. We saw that 2 slides ago. We know all the transactions that didn't commit, so we're just going to undo them. Except that we're not going to undo them one at a time. We'll undo them kind of all together. And that's the only hard part about hard. It's the only sort of cleverness in the undo phase is we're doing batch undo of a bunch of transactions. So redo starts from the oldest rec LSN, the oldest way that the database in buffer pool, that the buffer pool could be dirty relative to the database. We redo all that stuff in the log to make sure all those things in the log that changed are reflected in the database disk. And then after, well, really reflected in the buffer pool and the database disk. And then after all that, we undo, and then we're done. How far back do we have to undo? Well, any log record of any transaction that didn't commit needs to be undone. And those could be old. You could have a transaction that's been running for 17 years and still hasn't committed or aborted. Suddenly the database crashes. Now you got a 17-year-old log record you need to undo. And guess what? You have to go through it sequentially in reverse order, sort of. All right, we'll jump a little bit, actually. You'll see. Big picture. All right, but that's the big picture you need to understand. We'll go through the details. Repeat history, redo, then undo. Good? All right. By now, you should understand the purpose of essentially every piece of state, I think, in the picture of all the state. We haven't seen undo next LSNs and rec LSNs at play yet. We will see that. The only other thing to keep in mind that we didn't talk about is like, you're in the middle of doing logging and recovery. How long do you think this might take? Well, if you haven't checkpointed for a while, this could take weeks. Okay? Hopefully you've checkpointed recently and it doesn't take that long, but it could take a while. Guess what? How often do you think this code gets invoked? Every 6 months? Once in a while? I don't know. Guess what? This code might have bugs. And then it crashes. And that sucks. All right? Hopefully it doesn't have deterministic bugs. All right? Because if deterministic bugs, it'll always crash and then you'll never recover. But hopefully it might have non-deterministic bugs, in which case it might crash while you're recovering, and then you have to recover from the crash that happened during recovery. So everything about this recovery protocol has to be recoverable. So we have to be able to tolerate crashes during recovery, right? Which could also happen because you pull the plug. So that's what rec LSNs are going to be for. So we'll see that in a second. All right, let's take these phases one at a time. The analysis phase. Remember, the analysis phase starts from the checkpoint records. Okay? So we're going to reestablish knowledge at the time of checkpoint. We want to get back to where we were at checkpoint time. So we're going to take the transaction table and the dirty page table that we wrote in that checkpoint record. And we're going to scan the log forward from that checkpoint. All the things that happened since the checkpoint need to get reflected in those main memory data structures. So if we see an end record as we're going down the log forward, we're going to remove the transaction from the transaction table because we're totally, completely done with it. It committed or aborted. All its CLRs, if there were any, were written. If you see an end record, you don't even need to have this in memory in that transaction table. That's what end records are for. They shrink the transaction table. So that's what happens if you see an end record. All right, move along. You see another record. It's a typical update record. If that transaction is not in the transaction table yet, it better be now because we're beginning that transaction. Okay, so if you see a log record and that transaction doesn't exist in the transaction table, put it in the transaction table. Set the last LSN for that transaction to the current LSN we're looking at. And if it's a commit record, then we change the transaction status to commit. Right? Okay? Now, suppose what we're looking at currently is an update record. If that page that it's updating, P, is not in the dirty page table, add P to the dirty page table. And then for P in the dirty page table, make sure it's rec LSN. Since this is the first time you added it, it's rec LSN equals LSN. Is the current thing you're looking at. Only if that's the first time you're putting it in the dirty page table, right? So if you see a page not in the dirty page table, you put it in and you set its rec LSN to the current LSN in the log. If you go down and you see another update to P, you do not update the rec LSN. Okay? Because you want to keep track of that there's this time in the past that this thing got dirty. All right, so this is basically the protocol for scanning forward during analysis. All you're doing is updating the transaction table and dirty page table to reflect the state of the system at the time of crash. When you're done, when you get to the end of the log, the transaction table will tell you which transactions were active you might think at the time it crashed, but realistically there might have been a log tail hanging out in memory when the system crashed, and you lost that. That's just gone. So what this is telling you is what transactions were active at the last log flush before the crash, which is the last recorded history of this database. Right? Okay? That's what the transaction table tells you. And the dirty page table tells you which dirty pages might not have made it to the disk. They might actually have made it. We don't know, because we haven't gone and looked at the database yet. We've only looked at the log. Right? So it's possible that actually the buffer pool did write those pages and everything's safe and good. But to be conservative, the analysis we've done so far tells us all dirty page tables that might have not have made it to the disk, that might need to get redone. Okay, so we'll conservatively redo all those. All right, so now we're in good shape. We can redo everything and maybe a little bit extra, and we can undo everything. And we know which things to redo and undo. So that's the end of the analysis phase. All right, now we're going to look at the R, the redo phase, starting from the oldest possibly dirty page time, right? The time of the oldest possible update to a page in memory. We repeat history to reconstruct the state of the database at the time of crash. All this being done, by the way, in the buffer pool, so it's real fast. We're actually updating these page images in memory. We're not necessarily flushing right now, which means if we crash, we lose all our recovery work, but so be it, okay? So we're in the redo phase. You read log records. If they have an update, you reapply that update to the page in question in the buffer pool. You read the page into the buffer pool, you make the changes, and you go forward. If you see a CLR, that is the log record of a transaction that was aborting when we crashed. You do what it says. You help it abort that transaction, right? So you redo the aborting processes that were going on. You repeat history, including undos. Okay? And you scan forward from that log record containing the smallest rec LSN, and we talked about why start here. That's the oldest possible time that a page is different in the buffer pool than it was in memory. These are the redos we need to do. Now, one caveat. There's actually cases where we don't need to do the redo. So let's watch this carefully. For each update log record, or CLR, so those are the things that modify the database, it's got to give an LSN. We're going to redo it unless, and here's cases where we don't need to do the redo, the affected page is not in the dirty page table. During analysis, this page didn't show up in the dirty page table. Is that possible? How could something not be in the dirty page table? Yeah. It's a hard question. I think I know the answer, but it's a hard question. I'm going to postpone it for now, but you might ask yourself that question. While you're redoing, if the page is not in the dirty page table, that means the analysis said this page wasn't dirty at the time of crash. All right, I'll tell you what's going on. So the oldest rec LSN, right, which is where we start redo from, is for some page in the page table, some frame in the page table holding this thing. There may be other pages that got updated later, okay, but that got both logged and the database records got written to disk, right, that don't appear as dirty just because they got... Is that true? Let me not try to explain it on 2 feet. I will just tell you that if the affected page is not in the dirty page table, there's no need to redo it because it's not dirty. How that could happen, we will leave for another day. Hopefully Thursday, since that's the last day. Okay? All right, but if the affected page is not in the dirty page table, don't have to redo. How about this? The affected page is in the dirty page table, but its rec LSN is bigger than where we are in our redo phase. All right, this one, I understand. Okay, so we're going down the log, right? Marching along, down the log in sequential order. We get to an update, and we look in the dirty page table. It says, hey man, the oldest recorded change to this page was further in time than the log record you're looking at. How could that happen? Yeah?
You have a page that gets flushed to this, and then it gets reloaded, doing subsequent data on it?
Absolutely. So back before the crash, this page was modified, which generated the log record we're looking at, and then it was written back to disk, and then it was read back into memory, and then it was modified, giving it a higher rec LSN, and then a checkpoint happened and copied that rec LSN into the checkpoint record. So the checkpoint record remembers that this thing was not dirty at the time of commit, or it was dirty with a later rec LSN, right? So it's because it had a higher rec LSN in the checkpoint record is why it's not in memory now. And that's also the answer to the first bullet. The reason that page would not have been would not have been dirty in the dirty page table is because when we flushed the dirty page table during the checkpoint, page wasn't dirty anymore. It had been flushed to disk. Right? Does that make sense? When we do the checkpoint record, we get the contents of the dirty page table. And some of the stuff that got dirtied in the past did get flushed to disk, and some of it didn't. The stuff that didn't causes us to recover from way back there. But some of it did get flushed in the past. And when we wrote down that checkpoint record, we knew that it was clean, not dirty. Okay, so we're in redo now. You see a page that's not in the dirty page table, you say, oh man, at checkpoint time, that thing was already flushed to disk, so I don't have to redo it. Or you see something in the dirty page table that was dirty at a later time than the current log record. Again, my current log records updates had been flushed to disk at the time of checkpoint, so I don't have to worry about them. The third case is the expensive case. It's like, okay, I think I need to redo this thing because the dirty page table says that it's dirty. And you go to the database, you get that page off the disk, you bring it into the buffer pool, and you look at it, and its page LSN, which points to the log record it last updated this page, is later than you. It's later than the LSN we're recovering. Which means that indeed, your update did get flushed to the disk, and in fact, another later update got flushed to the disk too. So you don't have to redo your thing. You don't have to redo your thing because the database already reflects it, and it reflects something later. Right? So you don't redo the database if the database has already got your update. And that would be true if the LSN in the database, if the page LSN in the database is greater than or equal to the current LSN. Good? So those are all cases where you know that the database has already seen this update and recorded it. So we'll apply each update once during redo at most. Right? And if it's already been applied prior to crash, then we don't apply it at all. All right, how do you do redo in the case where you do it? Well, it's very simple. The page is in memory now because we checked that third condition, and indeed we decided we had to apply the update. It's in memory in the buffer pool. We apply we put in the after image of the change, right? The later version. And don't forget, set the page LSN of this page to the LSN you just played redo on. Right? That's the most recent change to this page, is the thing you just redid. But there's no additional logging for redos. Unlike undos, you don't log your redos. And we don't force it. So these redos are all happening in the buffer pool, which means if you crash, you have to do the redo phase over. Okay? So that's the redo phase. You just redo all the stuff that didn't get done at crash time in memory. Yeah?
When does like the start point for what you're looking at watch that does that stay the same until those people that
Ask me the question again with this slide up.
like I guess the place where if it crashes in the middle, would you just start from the same place and go to it again?
If it crashes during recovery and you assume we didn't take any new checkpoints, then you will start from the same checkpoint record you started from last time. Yeah. That's right. Now, some of your redos may have gotten flushed last time because the buffer pool might have forced those pages out after you redid them. And you'll discover that exactly in these cases we just looked at here. The affected pages, the page LSN of the affected page is greater than LSN. And that means maybe your redos from last time you tried actually succeeded in making it down to the disk. You'll still only redo everything once, but you'll check to see if you need to redo it in the same way. Whenever the buffer pool wants in the background. Whatever's fast for the buffer pool. That keeps the system performance separated from the system recovery, if you like, right? The buffer pool should do whatever's fastest, and the recovery system is going to make sure it's correct. Yeah?
If you can go back to the previous slide, we had the error list. If we have a page that we do an insert on, previous to the last checkpoint, and so it's in the dirty page table, it's all there. We do a checkpoint, and then we flush it to disk. After the last checkpoint, we go to crash. And insert's not an identical thing. So does that mean that everything we have to do has to be like we can't import like a normal just like diff where we say we inserted this? That might move other bytes around.
Great question.
How do we deal with stuff that's not identical?
That's the gloss on the question, right? So the simple version of the question for people on TV who couldn't hear is, shouldn't we be concerned about the fact that some of our updates may not be item potent? That means if you apply them twice, they may do something funny. You really need to apply them just once. The example that was given is if we do somehow insert things that move things around on the page. All right, which actually in the protocol we've described doesn't happen, but let's just assume there's non-item potent things. The key to this is that, in fact, when you look at the redo, these conditions here, these three, affected. This lecture hall is too big for me, man. I need a ladder or a laser, but that's less fun. The three conditions were under the unless ensure that we apply every redo exactly once. So if the redo has already been applied once, we will see that. We will see it either because the thing wasn't in the dirty page table at checkpoint, or the thing was in the dirty page table but for another reason, for a later reason. Or, third case, it was in the dirty page table, but when we looked at the database, it had already been reflected there. So that last thing should convince you, for sure, that we will never apply a redo twice, because we'll look at that page LSN and say, already been applied. Not going to touch it. So item potency is handled through the protocol and the LSNs, not through the contents of the page. We make sure that every redo is applied exactly once. And by the way, this is a standard computer science trick. If you have an action and you want to make sure it happens no more than once, you use IDs, sequentially monotonically increasing IDs to record when things happen. Right? And then you can compare the IDs instead of worrying about the actions themselves. So the same thing is done with network packets and TCP. Sequence numbers are used to make sure that you get exactly one of each packet and stuff like that. Very standard. And then you take the semantics out of the problem, and you just use IDs and counters to guarantee exactly onceness. Other questions about redo? You know what's going to happen next is undo. So before we move to undo, more questions about repeating history. Yeah? Yep, so let's do this on the board. There were 3 cases to check for redo. So it's the redo unless list. Should probably update the slides. Redo unless. 1, the dirty page table does not have this page. If the dirty page table does not have this page was not in the buffer pool at checkpoint time. And if it wasn't in the buffer pool, that means that this update got written to disk already. So we don't have to worry about it. After all, the checkpoint was telling us what pages hadn't been written to disk yet, and this page was not one of them. Sorry? So remember, what does the checkpoint process do? It takes a copy of the dirty page table and the transaction table, and copies them into the checkpoint record, and writes them to the log. When we start recovery, we read that log record back, that checkpoint record, and we load in the dirty page table. If it didn't have this page, that means it wasn't dirty at the time it crashed. So we don't have to redo it. It's been flushed. All those updates were flushed at the time of crash, right? All right, that's case 1. Case 2, the dirty page table does have the page, but rec LSN is greater than this record that we're redoing's LSN. What happened here? This means the page was dirty due to LSN, to the thing we're trying to recover. At some time, it was dirty. Our update was applied. Then it was flushed to the database. And then it was dirtied again by rec LSN. All right, so what happened in history must have been, because remember, rec LSN doesn't change. It's the first time the page gets dirty, right? So the transaction table we wrote to disk at checkpoint had a higher rec LSN than our current redo. That means at the time of checkpoint, our current redo was flushed to disk, or it would be the rec LSN. So what must have happened is this thing got dirty, because clearly we dirtied it. But then it got flushed to the disk so that when it got pulled back in, it got a new rec LSN, which is bigger than us. So we know that our write is on disk. So we don't have to redo our write. And then the third case is the direct comparison. The third case is the let's be careful case. Right? Check the database. And this is sort of the base case. If the page LSN on that page, after you pull it up from the database, is greater than this LSN, well, that's what page LSNs are for. They tell you the last update that's reflected on this database page. And it's telling you the last update to this page is later in time than you. So you're good. Don't reapply yourself. Okay? So those are the three cases. This is sort of ground truth. You can always go do this. Those two things save you the trouble of pulling this page off the database and checking. If those two things are true, then this would be true as well, but we don't have to go pull that page and check its page LSN. So that's another way of thinking of that. These are just more efficient versions of this third thing.
So for the second example, did the second, did the other one that deleted that get flushed also?
Not necessarily, it might have. And that's why we have to go to the third case in that. When we get to that LSN. When we get to this LSN, we read it off the database. We won't know if it was flushed or not. We'll have to go check the database.
So when we say the system flashes, do we assume the disk and the memory and the cache are still in the same state?
Good question. So when we say the system crashes, in our discussion to date, we've been assuming that the devices did not fail. There's no media failure. The disk devices are still there and still non-corrupt. All right, that's an assumption we made. Memory's gone. We're assuming there's nothing in RAM. Okay. You could use non-volatile RAM like flash, but let's just pretend that's disk. And in fact, typically that's the way it gets used in a database, just to treat it as disk. So you wouldn't put the dirty page table in flash. It's too expensive. I mean, it's too slow. Excuse me. There is the case where the database device has been corrupted, and then you just play the log back from the beginning of time. Right, because the actual checkpoint record isn't relative to any database anymore. There's no database. So if the database device crashes, you play the log from the beginning of time. What do you do if the log device has crashed? I mean, like media failure crash? You cry. Okay? And you hope that your database survives till you can get a nice checkpoint of it. Right, so one thing you can do is you pull the database offline and take a checkpoint, a physical checkpoint of it, literal physical checkpoint, and that becomes your beginning of time. And that's like your first log record from the future. That's what you can do. The way you make sure your log device doesn't crash typically is you duplex it. You have two devices, either because of hardware or just because you have the software routing all log records to two places. But most like commercial high importance databases have a duplexed log. So if one of the log devices fails, there's another one that picks up. Okay, which is also called RAID 1 if you want, which is just a mirrored disk. The disk, there's two disks that have the same writes. Right? And every log record, therefore, if we're going to pretend it's atomic, has to get to both of those things before it's considered flushed. Okay, so you do want your log device to be super rock solid. The other thing we didn't talk about yet is, what about like earthquake, right? What do you do? Well, your log and your database are probably in the same data center. What if the data center like burns to the ground, or your I don't know, IBM bombs Oracle's installations or something. Many financial institutions take their logs and ship them off or ship copies of them off to like a salt mine in Utah. This used to be true. It's probably not true anymore. They probably just replicate them in 16 places. But whatever, you do something that's the moral equivalent of geo-replication. And it's usually a little out of date because it takes a little time to take that log, copy it, and move it to Utah in the background. So it's usually what's called a warm replica. It's not hot. It's not exactly transactionally two-phase commit the same, but it's at least up to the recent past. Okay. Good. By the way, an excellent way to replicate a database is to ship the logs. You don't actually ship the database. The log is more compact. You just stream the log along. It's a good way to do replication of any kind in a database. We'll talk about that maybe in a grad class. All right, let's do undo. Undo. All right, we finished redo. The database is now in the state that it would have been in if we had been running, if we didn't crash. We just have a whole pile of transactions to abort now. So the naive solution for undo is any transaction still in the transaction table is a loser. It didn't commit through the process of running the log forward. We didn't see a commit record for it. So it's a loser. So all the losers will just do the simple transaction abort that we learned 4 slides ago. And that works. All right, that's correct. What's the problem with that? It's correct. So the problem must be that it's what? Slow, yes. All right, why is it slow? Well, think about what that protocol was doing. Let me illustrate through interpretive dance. Here's the end of the log. I'm about to undo transaction number 1. And now I have to undo transaction number 2. And now transaction number 3. You get the point, I think, yes? So what we'd like to do is like Fred Astaire our way through all of the transactions. Yes, all in one pass. Undo them all. Okay? That kind of hurt. Thank you. Arts and sciences, you know. Awesome. So the undo phase is just going to be a batch undo. And so we're going to have to kind of keep in our heads all of the things we're undoing at once as we take a pass backwards through the log. So instead of leaping through the log through prevel ascends, we're going to scan the log backwards, going to the next prevel ascend that any transaction has. All right, so here's how this works. At the beginning, we start and we say, who are all the losers? For all the losers, let's remember their last LSN. And in principle, there's a little copy of me standing on each one of those little hopscotch squares for each one of those LSNs. But I'm just remembering that in my head. I'm not actually in all those places, okay? And then I start at the biggest of those, and I deal with it. And it's got a prevel ascend, right? So after I'm done dealing with it, I know the next place I would hop to for this transaction. But maybe there's something in between that also needs to get dealt with. So I switch to that one, and I deal with that one first. So in essence, at any given time, I'm keeping track of where I am in all of these losers. And I'm taking the loser that's most recent in time to be undone, and I'm stepping to it next. So let's see how it goes. You choose and remove the largest LSN among 2 undo. 2 undo is the set of all losers. Starts out as the last LSN of all of them. Oh, I'm tired, too. If this LSN is a CLR, that means it was something we were undoing. We don't undo our undos, of course, ever. But if it was a CLR and its undo next LSN is null, that means it's the CLR of a transaction that was finished undoing things. This is the compensation log record for the first log record of some transaction. So all we need to do for this guy, we don't have anything more to undo. We just write an end log record for that guy. He's done undoing. If this LSN is a CLR and its undo next LSN is not null, then the next thing we have to do after this is the undo next LSN, right? So this thing already got undone. We have a CLR for it. So we don't have to do anything. We just have to remember that the next thing to undo is the undo next LSN of this thing. And we add it to 2 undo. You good? Those are the weird ones. The next one's easy. If it's an update, undo it. Well, in particular, write a CLR for it at the end of the log, modify the state in the buffer pool, and add its prevel ascend to 2 undo, right? And of course, that CLR that you generate is the typical thing with the undo next LSN and so on. And you just keep doing that until 2 undo is empty, which essentially has the effect of doing all those dances simultaneously back through the log, but at any given time, you're dealing with the thing furthest to the right. Okay? Question?
Would it cause problems if the order we do, all the reduce and unreduce, doesn't correspond to the original order of the transactions?
Wow.
It seems like we do all the reduce first and then undo later.
Well, yes. Interesting. So, let's see. I would like to repeat the question in a form. Let me answer the question, then maybe we can go back to the theme. So the theme of redo, remember we do analysis, then redo, then undo. And the question was, gee, it seems like that's not historical because that's sort of not how things happen. Things were undoing and doing at the same time in history, right? That's all captured with the CLRs. So in essence, when we replay history, we're redoing not only the forward progress of transactions, we're also redoing the undos that had been going on at the time of crash. So the redo phase of recovery actually gets you to a point where the mixture of do's and undos at the time of crash have all been done. And that's why it's repeating history. We've really done all of history, not just the forward progress history, but also the undo history.
So include those incomplete transactions.
That's right. And so now, because we've repeated all of history, all we have to do is undo stuff. Right. And we don't do the undos that already got undone, because they don't need to be undone. They only need to be redone. CLRs only get redone, right? All right. This is just a performance optimization on that naive dance I did, right? Or set of dances. All right. We'll do one example. Let me just look at my slides. How many do we got? Just a few. All right. We're going to be efficient. We're going to do it right now. All right. Here's an example of the recovery protocol. We're going ahead. This is the log, all right? And what we're going to do is we're going to play it forward from the beginning. This is an empty database. Okay, and we're just going to happily do our logging protocol. So the first thing that happens, we write a begin checkpoint on the empty database and an end checkpoint on the empty database, which contains an empty dirty page table and an empty transaction table, because there's no dirty pages and there's no transactions running. Okay, at LSN 10, transaction 1 comes along and writes a log record that says, I have written page 5. And its prev LSN is null because it has not got any previous LSNs. The next thing that happens in the log is log sequence number 20. So I numbered these with gaps just in case I screwed up and I needed to stick any in between. If you learn to be a basic programmer as a child, this is what you do. You leave gaps in between your lines. So ignore the fact that they're not sequential, right? They are increasing, which is the important thing. So first, there's log record 10, which is this update. Log record 20 is the next log record. It's transaction 2, and it's writing page 3. And it also has no prev LSN because it hasn't done anything yet, transaction 2. The next thing that happens is transaction 3 says, log sequence number 30, transaction 1 says, I abort. And the prev LSN of that log record is 10. Right? Because that's the previous log record of transaction 1. Make sense? At 40, we start undoing T1. And the first step of undoing T1 is to undo log record 10. So we're undoing T1 with LSN 10. What is the undo next LSN of log record 40? What would be the thing to undo after 10? Null, right? There's no more to undo for that transaction. So it's an empty undo next LSN. So what I've written for 40, it's the CLR. The thing it's doing, I'm being sloppy about. All right, I'm calling it, it's undoing LSN 10, whatever that was. All right? We wouldn't ordinarily write down LSN 10 in there at all. We'd write down undo next LSN equals null, right? And then the update, the redoable update. All right. T1 now is done because its undo next LSN is null, and so it writes an end log record. The next thing that happens, log record 50, T3 comes along, writes P1, prev LSN is null. This is the first log record for T3. Log record 60, T2 comes along with an update to page 5. The prev LSN for 60 is 20. That's the previous LSN of T2, right? At that point, the system crashes. Along the way, we were updating the transaction table and the dirty page table as we generated these log records, right? Which I didn't do. Ordinarily, we would do this interactively. I'd have one of you guys be RAM, and you'd be updating RAM, but I wanted to make this efficient. So as we're writing these log records, we're updating the last LSNs of the transaction table and the status. We're updating the dirty page table and the rec LSNs. And it's probably worth us going back and doing that on Thursday, now that I think about it, because if you don't actually work through this carefully, you get screwed up. So what we'll do on Thursday, I think, is we'll go through this example, which is just a plain old crash, and we'll manipulate RAM. And then what we'll do is we'll crash during restart, which is kind of a headache. All right, so we'll crash during recovery. We'll do the same thing. And that hopefully will give you the sense of how this all works together to do recovery. All right. And I think with that, we should call it a day. It's 1:30. So let me make a couple quick announcements about the final, which I will reinforce next time. So the final exam is a week from Monday. Next week, during class time, Tuesday, Thursday, there will be review sessions. The Tuesday review session will be up to midterm 1. The Thursday review session will be midterm 2, up to midterm 2 and recovery. I will on Thursday make very clear which topics are on the final. All right, not all of the topics that we did in the advanced concurrency control will be on the final. So I'll go through that on Thursday. I'll be very specific about what you're expected to know. Guest lectures will not be on the final. Okay, that material is not on the final. Any other highlights that we need to mention? Office hours and sections for next week will be posted on Piazza by Thursday, so you can make plans. We're going to not have them all at the end of the week, kind of where sections are scheduled. We're going to spread it out a little bit. I will have office hours as usual next week, but you'll see that on the schedule. Any other logistics questions that people have about the final? Yeah. The review sessions will be recorded and webcasted. I requested that. Any other questions? There will be office hours and section times that will be posted for next week. That will be posted by Thursday on Piazza. This week there's section as usual, unless your TA told you otherwise. And office hours as usual. Oh, last point. There will be a vitamin passed out at the end of this week, which is for your benefit only. You will not turn it in, but it will reinforce some of the material from Aries so that you can use it to study. See you on Thursday. Power cable.